How to Have a Quickie with Your Data, Part 1 is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. The two videos, How to Have a Quickie with Your Data, Part 1 and Part 2, quickly explain and demonstrate the three basic tools we will use to fit or characterize data with spreadsheets. Spreadsheets have a lot more data fitting tools than the ones we are going to cover in these videos, but this set will go through most everything that we need for the remaining DOFPro videos. The linked DOFPro stats videos are much more complete in discussing how to do data fitting. If you really want to get into the details, please go watch the stats videos on the playlist, which is linked on the website. Let's list some of the built-in functions in LibreOffice. The first data fitting functions that we're going to use calculate the mean or arithmetic average and the standard deviation from a set of values. They are the average and stdv.s functions. The second set of data fitting functions we're going to use calculates the slope and intercept of a dataset. They are the slope and intercept functions. The third tool we are going to be used is Solver, a multi-purpose tool that will, among other things, maximize or minimize a multivariate function. We will not demonstrate Solver until the second video. We're going to use it to do nonlinear least squares fitting of a multivariate function to a set of data. The steps in using Solver are as follows. First, you need to set up the fitting function. Then you need to set up the array of fitting values, and you need to keep the magnitudes of those fitting values roughly equal, within an order of magnitude or two. You then need to calculate the sum of the squares of the residuals, or the sum of the squares of the errors, depending on your mood. The SSE is basically just the sum of the squares of the differences between your measured values and your fitted values. Then you need to use Solver to minimize the sum of the squared errors by varying your array of fitted values. We'll begin with a brief video demonstration of calculating the average and the standard deviation of this set of data points that represents a set of noisy measurements of a single value. Here is the brief demo of how to calculate the mean and the standard deviation of the dataset using a spreadsheet. Column B is the data points. We will label the mean as mean, or you could call it average. LibreOffice does not have a mean function in it, but it does have an average, so we'll type in equal to average opening paren. Then we'll drag over our dataset and type a closing paren and hit return. There we have our mean. Now we want our standard deviation. We will do that with the label std period dev period, because the whole word standard deviation will not fit in there. We will set the cell equal to stdev.s paren, and then we'll select our dataset again, enter closing paren, and then hit return. There we have our mean and our standard deviation. The .s stands for sample standard deviation, which is the one you'd use on a set of sampled or experimental data. If you had the full population dataset, you'd use stdev.p. Next, we're going to do a demo for the slope and intercept functions. We have here 4 sets of data for second-order chemical kinetics at 4 different temperatures: 290K, 295K, 300K, and 305K. For second-order kinetics, the concentration varies with time as follows. The concentration equals the initial concentration divided by 1 plus the initial concentration times the rate coefficient times time. You can linearize this function by taking the reciprocal. You get 1 over the concentration equals 1 over the initial concentration plus the rate coefficient times time. If you plot 1 over the concentration versus time, you will find that the slope is the rate coefficient k, and the intercept is equal to 1 over the initial concentration. Now for the demo. Here is a brief demo of how to do a linear fit to the second-order dataset that we have here. The first thing that we need to do is take the reciprocal of the concentrations versus the times that we have. We need to label them somehow, so I'm going to use the concatenate function for the labels I enter in this cell. Equal to concatenate, open paren, quote, 1 slash, quote, comma. Then I'm going to select the cell containing CA290K, enter a closing paren, and hit return. The concatenate function adds strings together into a longer string. Text has to be in quotes, sometimes called double quotes, as opposed to apostrophes, which are sometimes called single quotes. I will select and drag to create the remaining labels. Next, I need to have the reciprocals of the concentration data, and to get the reciprocals, I'm going to type equals 1 slash, and then click on the first concentration cell. Then I can drag across and then drag down to create the reciprocals of all my data points. The model says that the rate coefficient k is equal to the slope of 1 over Ca versus T. We label this cell as slope paren k paren. We calculate the slope with the slope function. We type equals slope paren and then select our y values, the 1 over Ca's, and then type comma and select the x values, the t's. Since we use the same set of t's for all 4 sets of data, we'll set them to absolute reference by hitting the F4 key. Close paren and hit return. Then we can drag that across, and that gives us our 4 values for the rate coefficients for the dataset. We know that the intercept is 1 over CA naught, so we'll label the row title with int space paren 1 slash CA0 paren. We type in equals intercept paren and then select the y values as before. Type comma, select the x values as before. Hit F4 for absolute reference, type paren and hit return. We will drag this across to get all 4s as before. We'll label the next row as CA naught. Then we'll type in equals 1 slash and select the cell above and hit return. Again, we'll drag right to get all 4 CA naught values. We can do a quick check on how we did because I set this up so the initial CA naught values were the t equals 0 ones that were in the dataset. The first one should be 1, it's 0.986. The next one should be 2, it's 1.82. The third should be 1.5 and it's 1.59. The fourth should be 0.75 and it's 0.787. They're pretty good fits. To finish our fitting here, we need to do an Arrhenius plot. We'll label a row as natural log of k. Then we type in equals ln paren and select the first k value, then type close paren and enter. We'll drag it right to get all 4 k's. The next row we'll label as 1 over t, and then type equals 1 slash, and click on the first temperature, 290, and hit return. Dragging right gives us the other 3 reciprocal temperatures. The plot of log k versus 1 over t will have a slope of negative EA over r, and an intercept of log k naught. We'll label the row as slope and then type equals slope paren, and then select the ln k row. Type comma, and select the 1 over t row, type paren, and hit return. EA is the negative of the slope times r. We'll enter the label EA, and then type equals minus, select the slope, type asterisk, select r, and hit return. The activation energy used to generate the data was 100,000, so we're less than 1% off. K naught is the exponential of the intercept, so we'll enter a label for the intercept and then type equals intercept paren. And then select the ln k row, type comma, select the 1 over t row, type paren, and hit return. Next, we'll label a cell as k naught, and then type equals exp paren. Select the intercept, type paren, and hit return. We get 2.7 times 10 to the 17th, which is very close to the generating value of 2 times 10 to the 17th. The copy of the solution on the website includes plots to show how well the data is fitted with this model. In the next video, we'll show how to fit the same dataset using solver and nonlinear least squares. The takeaways from the video are: 1. Spreadsheets have built-in functions to calculate the mean and the standard deviation of a set of data. 2. Spreadsheets have built-in functions to calculate the slope and intercept of a set of paired data. Thanks for watching. This video was brought to you by the DOFPro team.